Okay, so this is the, I think, 9th lecture. Okay. So what we're going to do today is we're going to do Bayes' theorem. How many of you have taken a statistics class where you've done Bayes' theorem? Okay. You can spend your entire life on this theorem. Right? And there's actually a huge divide in the statistics community between the frequentists and the Bayesians. We're not really getting into that in this class, but there is an enormous number of things you can do with this result. And so what I want to do is I want to give you a sense of what Bayes' theorem is, how it can be used, and do one or two interesting examples. How many of you have seen Simpson's paradox? Okay, a few. So I'll probably have time to do an example of that today. All right, so what I want to do is I want to start off with where we were before. So Bayes. All right, so we had before the probability of A and B was the probability of A given B times the probability of B. Right? We proved this last time. There's another way to write the right-hand side. How else could we write the right-hand side? Yes?
The probability of B given A times the probability of
Good. We could just switch the roles of A and B. So if you want, just take the statement of where we had A, now put a B and just switch the order. And if you do that, now you get the probability of B given A times the probability of A. Last time I checked, A intersect B is the same as B intersect A, so these two things must be equal. And thus we get the probability of A given B, probability of B is the probability of B given A times the probability of A. Or you can solve, just so I did the same what I have here, the probability of A given B is the probability of B given A, probability of A over the probability of B. And now if I'm doing this, what must I assume?
Probability of B isn't 0.
Good. Probability of B is not equal to 0. So as long as the probability of B is not 0, we can find the probability of A given B in terms of the probability of B given A, and then the probability of A and the probability of B. So the way you should look at this formula is we have 4 events in play. B given A and A given B. Depending on which ones you can compute, you can use 3 of them to find the 4th. And sometimes it's easier to do one conditional probability rather than another. And that's the whole point, is if we can compute the probabilities of A and B, and we can do the conditional probability of B given A, then we can immediately pass to the probability of A given B. Okay? Now the question becomes, how do we calculate the probability of these events? A lot of times what we're going to do is we're going to use the theory of partitions. So I'll do a little bit of an aside right now on partitions. We've already seen partitions. So there was a reason why in the first day of class we did the basketball problem. It was a way to see, well, I guess that was the second day of class, it was the first real day of class. The basketball problem split the probability of Bird winning into a bunch of mutually disjoint possibilities. Bird wins on his first shot, Bird wins on his second shot, Bird wins on his third shot. Right? And so if we want to calculate the probability that Bird wins, we break it up into a sum of distinct events we then compute. And the idea is it's often easier to calculate the probability of these events than the probability of just in general Bird wins. It's very important that the events be distinct, so that they be disjoint. They can't both happen simultaneously. Can somebody give me an example of a situation where we actually broke things up into events, but the events were not disjoint? Yes?
Distributing the trump cards in bridge.
So distributing the trump cards in bridge. It's possible that you could have 1 and 2. Once we got conditional probabilities with that, they weren't independent. Good. There's another example. How many people are sitting where they sat yesterday? Yes. So what's the other problem? We split something up, and then we had to worry about things happening together.
Derangement.
Derangements. right? It's very easy to break it up into person 1 returns to the seed, person 2 returns to the seed, person 3 returns to the seed. But then we have to worry, what if 1 and 2 return to their seed? And this gives us the inclusion-exclusion. We gave a rough idea of why that worked. We'll probably do a little bit more on that on Friday. So it's very nice if the partitions are disjoint. So we say A1, AN, partitions, actually, I'll just leave it as dot, 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 partitions omega if the union of the AIs equals omega, AI intersect AJ is the empty set. So think of it as we're breaking our space up into disjoint subsets. I actually don't necessarily require them to be disjoint. I just require the probability of their intersection to be 0. Right? Because if an event has 0 probability, I really don't care about it. So you can weaken this a little bit. And now what we can do is if I want to know what's the probability that some event B happens, this is the probability of the union of B intersect AI. And the reason is the union of B intersect AI, I'm sorry, yes. So this gives me the part of B that's in A1, union the part of B in A2, union the part of B in A3, union the part of B in A4. Do I ever count any part of B twice? No, because there's nothing in 2 distinct A's. And no matter what I have in B, it's got to be in one of the AIs. Because the union of the AIs is omega. So you give me anything in B, it's in exactly one AI. So that shows that this thing here is contains B. And conversely, since each one of these is a subset of B, the union is a subset of B. So one of the best ways to show that 2 sets are equal is you show they're subsets of each other. So if X is a subset of Y and Y is a subset of X, then X must equal Y. So this is another way of writing B. But now we've written it as a disjoint union. The probability of a disjoint union is the sum of the probabilities. So it's the sum of the probability of B intersect AI. And for our basketball problem, B is the probability that Bird wins, and maybe AI is the probability that Bird wins on his ith shot. So I might want to allow myself to have infinitely many events. What kind of infinities am I allowed to use? Yes? Only countable. I can't have uncountably many events. We don't know how to deal with stuff like that. Okay? So the idea is that frequently, instead of doing something like the probability of B, I might split B up into a bunch of different disjoint sets. And each one of those might be easier to calculate. Okay. So this is the rough idea. And now let's do an example. I can't spell so much through TV. Tuberculosis. Okay? Don't want to go into too many details. I think we can all assume we don't want to get a really bad infectious disease. Okay? If you have a really bad infectious disease, what should you do?
Not be around other people.
Good. In fact, I know somebody did not come to class today because they were sick, and I appreciate that. I have 2 young kids, so in terms of diseases coming to my household, it's almost nonstop. It's much better than now that they're out of the children's center and you have all the sick kids blowing on birthday cakes. They're a little bit harder now. But what should you do if you have a really bad disease? Yes. Go to the doctor, right? And the doctor will probably give you some strong medicine. The medicine might be expensive, though. So we have finite resources. Should we give you expensive medicine?
Depends on how bad your disease is.
Outside of the jurisdiction of my class. I'm not going to talk about allocation, okay? I'll leave that for other classes. What we can do in this class, though, is talk about how likely is it that you're sick. So just because you test positive, does that mean you're sick? No, it could just mean it was a false positive, that maybe you are healthy, but the test is not 100% accurate. So then it becomes a very interesting question, which way would you rather err? Would you rather err and tell somebody that they are sick when they're healthy, or they're healthy when they're sick? Yes? You'd rather tell them they're sick when they're healthy, because you want to make sure that the people who are sick get treatment. Okay? As long as the treatment is not something like, we just cut off your arm. Something like that, then okay, then there's issues. But most of the time, it's much better to tell somebody that they are sick when they're actually healthy. There is some psychological issues and whatnot. These are really good things to think about. Let's say we have two tests. One test is more accurate than the other. Should we use it? Yes?
Only if the first test comes back positive.
Well, what's the first test?
The first test is less accurate.
So why should I use the less accurate test first?
Because it,
Or why wouldn't I use the more accurate test?
It depends on the cost.
It depends on the cost. My wife is a professor of marketing, so this will be a chance for me to actually have some intersection with her classes. How many of you have seen I think it was the Verizon commercials, Can You Hear Me Now? What happened to that person?
He's now working for Sprint.
He's now working for Sprint and saying, why pay 50% more for 1% improvement in service?
And then they have another commercial. Verizon has a commercial with Ricky Gervais. It's just like Sprint is lying on their commercial.
Oh, I have not seen the Verizon comeback. I have not seen the Verizon comeback that they're lying. I still think it was a strategic error by Verizon not to have in the contract for this person that you cannot do advertisements for our competitors. Because you've now become identified in the public mind with Verizon. And to now have this person doing commercials for Sprint is really bad.
I mean, he looks kind of different now.
It's a yellow shirt. He looks different, but cost matters. And so the big argument that Sprint is making is, yes, we're not as good as Verizon, but the difference is so small. Do you really want to pay all this extra money for this small improvement in service? If a test costs $1 and is almost as accurate as a $500 test, you probably want to do the $1 test. And then if the $1 test comes back positive, then you do a more expensive follow-up. And so the idea is to conserve resources. So in terms of the applicability, later on we're going to do generating functions, we'll prove the central limit theorem. Here's some really basic math that has direct impact in the real world. And we're trying to allocate healthcare dollars. Okay, yes?
Well, wouldn't you only want to do the second test if you're kind of in the middle on the first test? If you're very obviously positive?
Well, so a lot of tests don't have very positive. They're either yes or no.
You take the less accurate test first, and you gives you back negative if you.
Right. So then the question is, if it comes back negative, what if you actually are sick? Yeah. And then this you have to look at what's the rate of false negatives. Should you actually have two of these tests? And is the odds of two of them both coming back as a false negative? And again, it's a function of how much resources do we have, how much do we want to spend on this, how much of your time do you want to spend taking tests, and also what is the likelihood you actually have the disease? There are certain extremely rare diseases I'm pretty sure I don't have. I have not been in the tropics lately. I'm not going to really spend that much time testing myself for that. Other diseases, the Williamstown Elementary School, they have about 400 so kids. Last spring, one day, 99 I think kids were sick on Monday, went up to about 120 on Tuesday. By Wednesday, they said, this is ridiculous. Next week is spring break. We're closing school Wednesday at 1. No school Thursday, no school Friday. Do not come to any activities. We're done. So in a situation like that, okay, I think I might want to test myself. I may feel good, but there's a lot of stuff going on right now. So what I want to do is, let's say tuberculosis. Let's say 1 in 15,000 happen. I have no idea if these numbers are reasonable. I think I got them from Wikipedia maybe. So let's assume that there's a tuberculosis scare in our town, and assume, for simplicity, that the rate of infection in Williamstown is the same as the national average. So your probability of having tuberculosis is 1 in 15,000. Okay. Do we expect anyone to have it here?
Not really.
Not really. This is a small question. I expect at least 2 of you to have the same birthday. I do not expect anyone here to have tuberculosis. So we can continue with this lecture. Okay. So just to be safe, we go to our doctor to get tested for the disease. It has a 1% false positive and a 0.1% false negative. So what this means is 1% of the time false positive. It'll say you have tuberculosis when you don't. Okay. So now, every 100 people, healthy people, one test positive. Every 100 healthy have one test positive. And you have a 0.1% false negative, so you can figure out what that is. And now you test positive. So how scared are you? You just tested positive for tuberculosis. Do you think you have it? I mean, this is a pretty accurate test. Yes?
No, because of 15,000 people.
There's 15,000 people.
Only one of them would actually have it, but it looks like 150 of them would test positive.
Yeah, so this is getting into like the expected counts approach. Anybody ever watch Scrubs?
Yes.
Okay, Dr. Cox is wonderful. He has a lot of really great rants. One of my ones is he's yelling at people, when you hear hoof prints, or when you hear hoofs, don't think zebra, think horse. Think the more likely explanation. And then something like this, there are so few people who are infected, it's actually more likely that it's a false positive. Imagine the ridiculous extreme where it's 15 quadrillion. Always go to ridiculous extremes. So when you get the test back as positive, you should be a little bit concerned, but you should not be panicking, you should not be making out wills. But you should definitely get a more accurate second test. So let's calculate the probability. So Bayes' theorem. So it is very easy to write these things in the wrong way. The probability that we're sick, given that we test positive. Can I write a plus sign for positive? According to Bayes, this is going to be the probability that we test positive given that we're sick. We switch the order. Times the probability that we're sick divided by the probability that we test positive. Okay? So we need to figure out all these different events. All right, so I think we can delete all this here. So some of these quantities are easier to find than others. So just rewrite it over here. Ridiculous. So we want the probability that we're sick, given that it's a positive test, is the probability that we are positive and sick, the probability sick divided by the probability that it's positive. What's the easiest one? Yes?
The probability that you're actually sick.
So what's the probability that you're actually sick?
So 1 over 15,000.
We agree that the probability you're sick is 1 in 15,000? This is from the givens. So by given, the probability that you're sick is 1 in 15,000. Okay. Oh, the video might be upside down today. All right. So, 50,000. What's the next easiest? Yes.
Probability that it's positive given that you're sick.
Okay, so what is the probability that you're positive given that you're sick?
Well, it's the flip side of the false negative. So it would be 99.9%, which is 9 of 99 over 1,000.
Good. So we know that 0.1% of the time we get a false negative. So that's when a sick person tests healthy. So if you're sick, of every 1,000, one tests healthy, rest tests sick. So that's also coming from the givens. So the only thing that's left is what is the probability that we test positive, right? Does the givens tell us that? This is the only one that's not coming straight from the givens. we have to figure out how do we calculate the probability we test positive. So I just erased it, but we were talking about partitions. Let's break the space of people who test positive into two groups. What groups do you think it should be?
People that are sick, people that aren't sick.
People who are sick. So it's going to be the probability that you're positive and sick, plus the probability that you're positive and healthy. Okay. So, I'm writing it out like this. So how would we calculate the probability that we test positive and we are sick? Yes.
Well, we could use the fact that we have positive given that we're sick and the probability that we're sick. Because you know that.
So this would be like the probability of positive. Just want to make sure.
It's like PA intersect B equals PA given B.
Right.
B.
And so I think what we do is probability is positive, given that we're sick, times the probability that we're sick,
And we know both of those already.
plus the probability we're positive given we're healthy, given that we're healthy.
Yeah.
So the idea is we're using the probability of the intersection, we're writing it as conditional probabilities. And the whole point is we want to keep writing things in such a way that it's going to be easy to see. That these calculations will be easy. What's the probability we're sick? 1 in 15,000. What's the probability we're healthy? 14,999 over 15,000. All right. What's the probability we test positive given that we're sick? I think we've already done that, right? That's 999 out of 1,000. And now the last is, what's the probability we test positive given that we're healthy? Yes? 1 over 100. This is the last given that we haven't used yet. We've used everything else. And so we used partitions to break up the probability that we were positive in terms of simpler events. So again, I would much rather do a lot of simple problems than one hard problem. And so when the dust settles, we now just feed everything in. And now it's just algebra. Okay, so feed in, do algebra. And at the end of the day, the probability that you are sick, given that you test positive, is 0.0066 approximately. I'm not that worried. Okay? So it's really good to know this. So, I'm hoping that later in life you will not test positive for a rare, deadly disease that has a high mortality rate. But if it does, at least be comforted for a couple of minutes while you're waiting for that second test, and think back to this class. Okay? There's other reasons why you want to choose to err to certain sides rather than others. For a lot of medical things, you don't want people to stop treatment too soon. And so you'll often tell people you need to take it for a little bit longer just to be safe. But you really want to think about how the math can be used. And so here it's allocating resources. Okay, any questions about this? I actually don't like this method of proof of this problem. It's not bad. I really much prefer the expected counts approach. And so what I want to do is let's do this problem again from an expected counts perspective. Okay. So this is probability of being sick. Probability of sick over. So let's do expected counts. So this is the first time we're doing an expected counts problem that's 1, worth doing, and 2, not immediately immediately clear how many people we should use. Okay. No one really cares about fishing for trout and bass, and if you caught a fish, what's the probability it's a trout? And it was really clear there how many fish we should assume we caught, and I multiplied by 100 to be safe. How many people should we start off in our population? Yes?
15 million,
15 million? Why 15 million?
because 1 in 15,000 have tuberculosis, and 1 in 1,000 of those people has is a false negative.
Yes, we've got 1,000 or 1 in 1,000 of the false negatives, and so I want to have at least 1,000 sick people. So it seems like 15 million is a good number of people to start with. Okay, we could have done 150 million to be extra safe. I think 15 million is more than that. So we'll start off with 15 million people. And now let's split. There's going to be the sick people and the healthy people. So we're doing it the same side of this. Yes, same way as the. How many people will be sick? 1,000. How many people will be healthy? 14,999,000. Okay. Of these sick people, how many will test positive? 999. How many will test negative? 1. Right? So this is telling you probably the 15 million is a good way to go because we end up with just one person in the category. We don't have a fraction of a person. Wouldn't it have been troublesome if we had a fraction of a person? It would be annoying, but would it really make a difference? No. I like to have nice round numbers though. So 15 million is good to start with. Let's look at these. How many will test positive? How many will test negative? So we have a 1% false positive. Out of every 100 people, 1 tests positive, even though they're healthy. Yes?
149,990.
Yeah, basically we drop 2 zeros. So we drop 2 zeros, it becomes 149,990. And then how many of them will, I don't even know if I even bother, I did bother right here. 14,849,010. I like the 10. Okay, so we've done everything correctly. This is the breakup. So now let's look at the people who test positive. The people who test positive, we have the 149,990 who are healthy, and we have the 999 who are sick. So if you test positive, what is the probability you're actually sick? 999 divided by 149,000. So probability you're sick, given that you test positive, is 999 over 149,990. Or approximately 1 in 150. Yes?
Wouldn't it be 149?
Oh, plus, yes,
Yeah.
plus, yes, plus 999, yes. You absolutely have to add the plus 999. I am just dropping it. Why am I dropping the plus?
Yeah.
It's not going to really change the probability. It absolutely should be here. It's approximately 1 in 150. So let's think about how this refines your expectation of being sick. Before you do any tests, how likely do you think it is that you have tuberculosis? No, be more specific. We can be more specific for this problem.
1 in 15.
1 in 15,000, right? Because you will assume that you're just as likely to have tuberculosis as everyone else. Now you do this test, and now you get back a positive result. And now you refine your estimate to approximately 1 in 150. It's still unlikely, but it's significantly more likely. And if you multiply 150 by 100, what do you get approximately? The 15,000. Okay. What if we did the crappy test twice? Can we do the crappy test twice rather than doing the expensive test? Won't that save money? Yes.
We don't know if testing twice is in the
good. We do not know if testing twice is independent.
Like maybe the same person will always
Absolutely.
have a false positive.
Absolutely. And so it could be that certain tests don't work on certain people in the population. I have, this is even further, but some of my liver enzyme numbers are just not the same as other people's. And that could affect certain tests. So you've got to be very careful to see, are they independent events? If they are, then you might want to do the crappy test again. Or maybe do the crappy test 3 times. Maybe it's better to do the crappy test 3 times. There's also a limit to how many times people are going to let you keep freaking them. And you might want to just move on to something else. But there's a lot of really good stuff in this problem. And again, you can spend an entire statistics course doing Bayes again, trying to pass from knowledge from some probabilities to others, and refining your estimates. Okay. Any questions on this? Okay. What I want to do now is I want to just briefly mention Simpsons Rule. There was a very famous article by Ken Ross, and so I will use his numbers even though I am a Red Sox fan. Okay. So, Simpsons power of powerful. So does everybody know what batting average is in baseball? So it's basically however many at-bats do you have, how many hits do you have, and then you do hits divided by at-bats. You can't have more hits than at-bats, so your batting average is always less than 1. Okay? If it's a walk, it doesn't count towards the at-bat. We don't really care about that. We'll assume that somebody either gets a hit or they get out. And here's the very strange thing. And we have 2 people. We have Derek Jeter and we have David Justice. I don't know if these people were chosen because they have the same initials. It just might be very convenient that way. In 1995, Derek Jeter's batting average was 250. And David Justice's batting average was 253. In 1996, Derek Jeter did much, much better and moved all the way up to 314. Any Yankee fans? Okay. When did Derek Jeter really come up?
Goodness knows, I don't remember because I was probably that 3 or 4.
My son was following Red Sox when he was 2. That's how he learned to bat lefty because he liked David Ortiz.
My
A
dad's
true
a Mets
fan
fan.
would know.
My dad's a Mets fan, so.
It doesn't matter. Okay. Yes.
96, right?
96. Well, I mean, he was clearly Derek Jeter was in the major leagues in 1995. So he was in the major leagues in 1994, 1990. See, this is where some historical knowledge would be useful. In 1996, David Justice batted 321. Who would you rather have on your team? Using just the information on the board. David Justice, right? This number is bigger than that number. This number is bigger than that number. Each year, David Justice is doing better than Derek Jeter. I would much rather have Derek Justice. I mean, not Derek Justice. Yes, Derek Justice. However, if you look at the combined, Derek Jeter's combined batting average for the 2 years is 310, and David Justice's combined batting average for the 2 years is 270. And this is why it's called Simpson's paradox, because when you look at this, this looks absurd. You know, in each year, Justice is doing better than Jeter, but on average, Jeter is better. So if you've seen Simpson's paradox before, you're not allowed to answer now. This is for people who have not seen Simpson's paradox. I believe this is actually not in the textbook, so this is something new, value added for today's lecture. Okay? What's going on? Yes?
So Derek Jeter clearly didn't have many at-bats in 1995.
So his real rookie year was 1996. He had a couple of at-bats in 1996. So if you look at at-bats, he was 12 for 48. Your 48 at-bats is not a statistically significant sample. Justice, however, had 411 at-bats and got a hit 104 times. In 1996, Derek Jeter played a lot more. He had 582 at-bats, and he got hits 183 times. Whereas over here, Justice had 140 at-bats and had hits 45 times. So if you look at the combined, he has 551 at-bats with 149 hits, and Derek Jeter has 630 at-bats with 195 hits. I apologize for not memorizing these numbers, but they involve a Yankee player. I'm just not going to commit that to memory. Okay? So when you look at this, if you just look at the combined thing, it's clear that you want to choose Derek Jeter. But it's a function of how the hits and at-bats were distributed across the 2 years that you get this paradoxical result where locally, Justice beats Jeter in average, but globally he doesn't. So this gives you a real warning about statistics. Some of you may have heard of the phrase, there's lies, there's damned lies, and then there's statistics. You can manipulate people very easily. Team has won 3 of the last 4 games. Okay? If a team has won 3 of the last 4 games, their winning percentage is 75%. Is the team playing well? What do you think? Yes?
If you say it, like 3 out of the last 4, they probably didn't win the one before that.
Right. If they had won 5 games ago, what would I have said? They would have won 4 of the last 5. So I'll clearly, if they'd won 5 games, the game 5 ago, I would have said they've won 4 of the last 5. So we know, if you look at their results, if you go back 5 games, there's a loss. Do we know anything else? We know 5 games ago they lost, yes.
You know the 4th game that they didn't lose?
Right.
Otherwise, they would have just said they won the last 3.
Exactly. If they had lost their 4th game, I would have said they've won 3 in a row. Now, in here, we have 2 wins and 1 loss. So if you look at the last 3, they are 2 for 3, or 66%. And if you look at the last 5, they're 3 for 5, or 60%. It's very easy to manipulate people's expectations of what's going on by what information you choose to emphasize. Okay? So here, as soon as I say 3 of their last 4, unless we've only played 4 games this season, you know they've lost 5 games ago. So the whole purpose of this is to just warn you about the need to be careful. Okay? So averages is a very difficult thing. When you're trying to add averages across years, it matters how many observations you have. Now, another thing we could have done is we could have said, I don't care how many at-bats Jeter and Justice had in each year. I'm going to consider each year as accurate as the other, and I'm going to take just the average of the 2. So I would say Jeter's average is 1/2 of 250 plus 1/2 of 314. This is not a good thing to do because let's say this is as accurate of a measurement as this. The more data points you have, the more accurate the measurement should be. So with only 48 data points here, I don't think it's that accurate. Similarly, this one has 3 times as many data points as that one. So you really want to be aware of these issues. Any other questions about this? Okay. So this basically finishes up chapter 4. By the time we finish chapter 5, that will be a good time for an exam. So you'll be aware that there's an exam coming. It will be at least a week away, but probably not more than 2. Right? It will be a take-home exam. It will be open book, and it will be restricted internet. So the internet is my homepage and anything directly clickable from the Math341, Stat 341 homepage. Nothing else exists. Okay, so if you've seen the movie Zorro, with the circle, nothing exists beyond that. Okay, so this means you don't have to memorize things. This means you don't have to have all these formulas and facts at your disposal, but you have to know how to use them. If you want to take notes and have notes available, that's fine. But do not print out other textbooks and stuff like that and have those, okay? That's not permissible. Okay. So we have time to do a little bit more. Let's do inclusion-exclusion, and I'll save ABBA for Friday. And if anybody has a favorite ABBA song and a favorite language for the ABBA song, if you email me, I will try to get that for Friday's lecture. All right, so we're going to do inclusion-exclusion. So we did this with derangements. So the probability of A1 union AN, this was the sum of the probability of AI minus the double sum of the probability of AIJ plus the triple sum of the probability of AIJK, blah, 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 blah. Okay, so this is our formula for probabilities. If we're in the lucky situation, the fortunate situation, where all the events at the same level have the same probability, if all have the same probability at a given level, then we get the probability of A1 union AN is equal to n choose 1 probability of A1 minus n choose 2 probability of A12 plus n choose 3 the probability of A123 yada yada yada. Okay? So we talked about this before when we did derangements. And I gave some rough heuristic as to why this should work. We've got a couple of minutes left now. Let's actually prove why this formula works. This is a great way to count. It replaces a very complicated event with a chain of simple events. And frequently this assumption that all things at a given level have the same probability holds. So this is not an unreasonable assumption to make. Okay? So the main thing we want to make sure we do is we don't double count, and we count everything exactly once. So if I had to say what the most common mistake students make in probability, it's not counting correctly, either double counting or omitting. We want to make sure everything is included once and only once. But when we look at this, we're clearly counting things multiple times. So I can't say I'm only counting something once, but I'm doing assigned counting. Sometimes I count it with a plus, sometimes I count it with a minus. And so what I really care about is how many times net is it counted. So let's say x is not in A1 union AN. Is x counted on either the left or the right-hand side? Not counted at all, right? Not on either side. Say x is in A1 and nothing else. Then on the left-hand side, we get it once. How often do we get it on the right-hand side? So how often would we get x on the right-hand side? Yes. Once. Just once. It's only in A1. So on the right-hand side, we would also get it once. Let's say x is in A1 and it's in A2, nothing else. How often is it on the left-hand side? Once. Right? The left-hand side is just the union of A1 through AN. It's always going to be on the left-hand side once. On the right-hand side, we get once because it's in A1, once because it's in A2, and then we subtract 1 because it's in A1 too. And 1 plus 1 minus 1 is 1. Let's say now x is in A1, A2, A3, nothing else. So as always, the left-hand side is 1, the right-hand side, now what is it?
1 plus 1 plus 1.
So 1 plus 1, I'm going to write that as 3 choose 1. Right? It's in A1, it's in A2, it's in A3. Now I have to subtract it. It's in A12, it's in A13, and it's in A23. So I now subtract off 3 choose 2. And then it's in A123. That's 3 choose 3. And so you get 3 minus 3 plus 1 equals 1. And so in general, let's say x is in A1, A2, dot, 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 AK. So, and nothing else. And so, continuing to bore the people who are in this room for 2 straight hours, this is something we talked about in operations research earlier today. If you're in exactly k of these A's, why not make life easy and just say it's the first ones? Otherwise, what I would have to do is I'd have to introduce indices. It's in I1, I2, I3, IK. It's in k of them. Well, it doesn't really matter which k. Let's relabel the indices so it's in the first k. It just simplifies the counting to have it in the first k. So if it occurs 5 times, let's say it's A1, A2, A3, A4, A5. Not A1, A2, A5, A7, A12. Okay? So let's count how often it occurs on both sides. How often does it occur on the left-hand side? Once. Fine, that's not so bad. The right-hand side. What's the first term?
Choose 1.
I'm sorry?
K choose 1.
K choose 1. I was actually thinking 5 choose 1 for a moment because I had specialized K to 5. Yes. So it's in. I have I have K sets A1 through AK where it's in. I can choose any one of them. How often is it in 2 of them? Right? K choose 2. So I subtract off K choose 2. And I add in K choose 3. And I subtract off K choose 4 plus or minus K choose 4. Okay? Anybody know what that sum equals?
1?
1, of course it equals 1. So we just need to prove this. And here's the proof. If you look at 1 plus 1, 1 minus 1 to the kth power. This is probably the easiest multiplication I can give you. What's 1 minus 1 to the kth power? 0. And now when you expand this out, you get k choose 0 minus k choose 1 plus k choose 2 minus k choose 3 plus or minus k choose k. And the reason is when you expand this out, I'm using x plus y to the k is k choose 0 x to the k plus k choose 1 x to the k minus 1 y plus k choose 2 x to the k minus 2 y squared, and so on. This is the binomial theorem. So we talked about the binomial theorem earlier. We talked about Pascal's triangle. So if I just take x equals 1 and y equals negative 1, we see the terms are going to alternate in sign. And if you look at this quantity here is the negative of what we want here. And k choose 0 is just 1. So 1 minus the right-hand side equals 0, for the right-hand side equals 1. And that's the proof of inclusion-exclusion. Okay? Any questions on this? So we finally got some dividends of the binomial theorem. It's not just to do derivatives in calculus, it allows us to prove inclusion-exclusion. All right, so we will now move on to chapter 5 on Friday.